This video is going to be the last part of our process for building box diagrams. At this stage in the game, you should already be able to fill a box diagram appropriately using filling rules. But on tests and quizzes, you will not have that blank document ahead of you. As a result of that, you'll need to be able to recreate that document using the rules and tricks we're about to talk about. So again, let's quickly go over the learning objectives of this video. We're going to start with a discussion of what this thing, the grid, really is. As I already mentioned, it's kind of just a trick used to figure out what the order of orbitals is in a box diagram. We'll talk about the setup of that grid, and then finally, as a result of that setup, it's going to generate a list of orbitals for us. That list of orbitals is ultimately what we're going to use to recreate this picture over here. These orbitals happen in a very particular order. It's the same order every time. As opposed to trying to memorize this order from bottom all the way up to top, we're going to use this grid thing as a way of generating that list for us. Let's start with a quick definition of what the grid actually is. It's basically just a simple tool used to determine the order of orbitals in the Schrödinger model itself. If you recall, this order is somewhat complex due to the fact that as orbitals expand from their original rings and get to higher and lower energy levels, we start to get this overlapping process that we see here between the 3d and the 4s orbitals that starts to happen. You can imagine too, as I started introducing a ring 5 and a ring 6 into this process, that overlapping is going to get more and more complex. Trying to remember, if you recall, we fill electrons in order from lowest to highest. We do the same thing with the Schrödinger model, but trying to remember this order of lowest to highest with all of these overlaps is very complex. Hence the need for a tool to help us remember what that order actually is. Now before we get started, there's a couple other things I want you to recall. This will be coming into play later as we go to put all this stuff together. S orbitals. If you recall from the pictures we drew, there was only one type of S orbital, which means all S orbitals simply need one box. P orbitals had 3 different pictures, there were 3 boxes. D orbitals had 5 pictures, there were 5 boxes. And finally, F orbitals had 7 pictures, therefore there's 7 boxes. Hopefully you remember this diagram over here to the right, and it's showing you all those pictures you drew. Each one of these pictures represents an orbital that can house electrons. Therefore, we need a box to represent each one of these. Every time you draw a D sublevel, you're going to draw 5 boxes with it. P sublevels always get 3. S sublevels always get 1, etc., etc. So as we put this diagram together, this is stuff you're definitely going to have forefront in your mind. Let's talk about the setup of the grid itself. The first thing I'll talk about when we talk about this topic is the fact that the grid itself doesn't really seem to have a whole lot of chemistry or science behind it. It's simply just a tool for helping you figure out what's going on. I'm sure if we investigated things further, there'd be a very good reason as to why all of this works the way it does, but that's not really that important for us. What is important is how to use this device in order to generate a list of orbitals that are in the correct orbital. So to start, you're going to need a layout similar to the one I have here. Notice we have four real columns to work with and then a certain number of rows. The number of rows you need depends on the size of the atom. In your columns, you're going to list your orbital names in order. So we have S, P, D, and F. In your columns, you're going to list the principal quantum number or ring number of each atom, of each electron. 1, 2, 3, 4, 5, and 6. And as we said, this list can go on and on and on depending on how big your atom is that you're working with. 6 or 7 is generally as far as we usually need to go. Now to fill this grid in, we want to write in the actual name of an orbital at the intersection of the letter and the number. So for example, at the intersection of this letter and one number, we end up getting a 1s orbital. At this intersection, we end up getting a 2s orbital, etc., etc., etc. So we fill in this whole column. We then go to repeat the process for P. We want to fill in all these boxes, but you need to remember that there's no such thing as a 1p orbital. The first ring splits into only one orbital, therefore this orbital doesn't exist. Any orbital that doesn't exist, we're going to leave blank. And that's actually true for 1d, and it's for 1f. So we'll just put little x's in there to remind us to leave those blank. We'll continue for row 2. Row 2 splits into 2 orbitals, a 2s and a 2p, so we will want to write those in, but there's no 2d and there's no 2f. Ring 3, if you recall, splits into 3 different sections, so we'll write the 3p and the 3d, but we'll leave the 3f out. And then finally, once you get to ring 4 and beyond, we're going to use all the boxes. So that's going to be 4p, 4d, and 4f, 5p, 5d, and 5F, and finally 6P, 6D, and 6F. Again, if we were working with larger atoms, we could do a row 7, a row 8, etc., etc., etc. Generally speaking, that's usually not too necessary. Now we've made this setup here, this grid thing, but we still haven't used it for anything useful in terms of creating an order of orbitals. Well, that's because we're not done yet. The next order of business now is to draw in some diagonal arrows. And again, I will reiterate, this all seems very strange. This all seems out of left field, and that's because it is very strange and out of left field. It's simply a trick that generates a useful list for us. The why of how this trick works isn't nearly as important. So here's how it works. You got your grid set up. You're going to draw a dot here in the top right corner of the first box, and you're going to draw a diagonal line through the box, making sure to intersect corners very, very carefully. It's very easy to wander off in the wrong direction. So I drew my arrow here from the top right corner to the bottom left corner. I'm going to repeat that process in the next box over. This one's going to go through 2 sets of boxes. I'm going to repeat again. Again, we're going to travel through a couple boxes here. I got a little sloppy there. Try and be careful. And we're just going to repeat this process all the way through our diagram. Now you'll notice I stopped here when I got to 6S. If I want to continue further, when I drew this diagonal line, it would go into the 7 row, and I would need to have the 7S data. If you want to go further like that, we would need to continue this, but we'll stop our diagram or our discussion here with 6S. Now let's go back to the beginning of this whole thing. We still haven't generated that list I keep talking about, but that's the part we're going to get to now. The last piece of this puzzle is simply following the arrows that you created. We started here and we follow this arrow. As we intersect an orbital, we're going to write it down in a list. So the first orbital we hit is 1s. When you get to the end of one arrow, go back to the beginning of the next. We're going to follow this along, and the next orbital we hit is 2s. Get to the end of the arrow, go to the next one. We're going to get 2p and 3s, and then we're going to get 3p and 4s, and then we're going to hit 3d, 4p, and 5s. And again, I'm just following these arrows one at a time. I just went down this one, 3d, 4p, 5s, and then finally to wrap things up, we're going to have 4d, 5p, and 6s. And again, this list goes on and on and on. Generally speaking, though, this is as far as you're actually going to need. So what we've done now from this funky little diagram that seems to have nothing to do with anything is we've generated a list of orbitals in order with all that wacky overlapping business that we were talking about that we can now use to put the correct boxes in the correct places to recreate that blank box diagram document that we have. If you don't believe me, if this doesn't seem to make sense, go back and check your blank box diagram, match up this order of orbitals here to the order of orbitals listed on the left side of your sheet, and you'll find that they will match perfectly, and they always, always will. So what we've created now is an order of orbitals needed for the box diagram. That order is going to look like this, and the good news is that it never, ever, ever changes. It's the same order over and over and over again. You can take the time if you choose to memorize this. I don't think that's a wonderful idea, but instead I think the better way of doing it is, again, using the grid. It's going to always generate the same exact list for you. You'll generate this once for a test or a project or a homework, and then you can use the same exact list over and over and over again for other problems and other experiments. Just to tie all this together then, at the top of the page we have our list that we generated from our grid. We'll now go to the bottom and actually use it to put together the box diagram itself. Our first orbital on the list is 1s. If you recall from before, a s orbital gets one box, so we'll draw in one box and we'll label it 1s. Our next orbital then in line is 2s. One box again for an s orbital. Doesn't matter that it's 2s or 1s, it's still just an s. And then we get to 2p. P orbitals always get 3 boxes, so we'll draw on all 3 of those and label it as 2p. Then we'll have 3s. Then we'll have 3p. We'll do 4s. And then finally we'll end with a d orbital. Just like we talked about with our list, d orbitals always have 5 boxes in them, so regardless of what you need, we'll draw on that 5, and this will get us 3d. And again, we could continue this diagram up and up and up and up and up, depending on how big our atom is. Once you have this grid recreated, you'll go back, you'll follow your rules, you'll put electrons in the appropriate places, depending on how many electrons you have, and etc., etc., etc. You'll be able to fill this whole process in. So again, We start with the idea of the numbers of orbitals per level. We use the grid to figure out what order those orbitals go in, and we use all that information combined to create a brandy new blank box diagram for any particular problem we're going to need. That's pretty much it for our video. At this stage in the game, you should be able to create the grid itself, fill it in with the appropriate letters and numbers, use those diagonal downward arrows to generate a list of atomic orders in order of increasing energy, and ultimately from that create a blank box diagram from that list of orbitals. With that information, you should be able to do all the stuff we've been doing all along with box diagrams, but now you should be able to do it without that blank box diagram template.